All right, so we've got this one. The only difference between this one and the one where the cable is like attached at some angle like that is that this one pushes, that one pulls, right? So they're solvable the same way. Okay, so this rod here is exerting a force right here. Let's see if I can draw this that way, right? Let's see, this angle is 38 degrees, right? So this angle here would be 38 degrees. So that unknown force is at 3.2 meters, and it makes a 38-degree angle with the rod, okay? It has a component that is this way. I'll call it F in the x direction, right? Which is, that is equal to F cos 38. And then it's got a component in the y direction, which is F sine 38. I'm getting that from SOHCAHTOA, right? This is the right triangle. This is the hypotenuse. And so the hypotenuse times the sine is the opposite side. Hypotenuse times cosine is the adjacent side. That's what I'm doing there. Okay, our other forces acting on this thing are, of course, force of gravity. So we got 3 times g, where g is 9.8. Right, so 3 times g, and then where is this guy? The box is centered 1.2 meters, so this is at 1.2 meters. We've got the force of gravity from the beam. That's 3g, but this one is 4g, right? 4 times 9.81, right? And then that is at, let's see, it's 4-meter long beam. So I do believe that if it's 4 meters long, that the center of the beam would be 2 meters. Okay, so we've got all the forces. We've got all the forces acting on this beam. We're going to torque about the left side. We made that decision when we started deciding where these distances were, right? 2 meters from the left side, 3.2 from the left side. It's always from the side where there's a pivot. I guess I'll put that on the left side, right? Okay, so our torque expression looks like this. We're doing R times F, right? So the first one we come to is a positive torque, clockwise torque from this one, right? And that is 1.2 times 3g. The next one is also positive, so we got positive 2 times 4g. And that's at a 90-degree angle, so we don't have to worry about any sign of anything. Then we've got this guy exerting an anti-clockwise torque, so we go minus 3.2 times whatever the force is times the sine of 38. Because it's not perpendicular, it's at some angle like that, right? Okay, and then that equals 0. Okay, so let's bust, I think I'm going to bust this out, divide by 3.2, divide by sine of 38, right? Okay, so 1.2 times 3 plus 2 times 4 times 9.81. 113.68 is this, and then I'm going to divide by 33.2. Divide by the sine of 38. 57.702. Getting a slightly different answer here. Okay, so the force is newtons. I'm wondering if I messed up on one of these things. Oh, I didn't do 9.81. Okay, so hold on. 11.6 times 9.81. That was the difference. Divided by 3.2 divided by sine of 38. I just did 9.8. Oh my gosh, 57.76 newtons is what that is, right? And that's why it rounds off to 57.8. Okay, let's see. So that is what that is, right? Okay. Now let's set up our, need space here. It's like, whoa, we're running out of space. Okay, let's set up our x expression. Our x expression says, what do we have? we've got this guy, right? We've got positive force in the x direction, so positive F cos theta, and then we've got the wall here. Okay, I'm guessing that the wall has a force that is, I'm sorry, the wall here, sorry. The wall has a force that is up, right? And then it also has a force that, well, you know, since that one's to the right, I bet this one's to the left. But let's just guess that the wall is pushing out, just like we always do, right? So we have wall in the x direction, and then we have wall in the y direction, right? So I'm going to say F cos theta plus wall in the x direction, 0. This has got to be positive, right? So store that guy. Store that in F just for fun. Okay, so take that guy and multiply by the cos of 38. And I get that it's 45.516 plus whatever the wall is exerting in the x direction. 0, well, this clearly, the force in the x direction has to be negative 45.516, okay? Newtons, which means it's to the left. Your other clue is that this rod would be pushing up into the right, so the wall to counteract that would have to pull to the left, okay? And then in the y direction, our equation looks like this. We've got the wall in the y direction. We've got minus 3g, minus 4g. That's the weight of the box, weight of the beam. And then we just take this side here, the F sine 38. So plus our force, which is 57.76 sine of 38. And then that's got to be 0. Okay. So notice I substituted the 57.76 for that guy, right? Okay, so let's see. To do this, I guess I'm going to go 7 times 9.81. That's 3g and 4g, right? Is 7g. Okay, minus the force times sine 38. Is that right? 33.108. The fact that it's positive means it's up because we guessed. At most, we guessed that Wx was in the right direction. We got negative, so therefore it's left. Ta-da. Would have been kind of fun to put, if you put that thing out far enough. Now, if you put it in close enough, that is, if you keep moving it this way, eventually this becomes like a tipping point, and Wy would actually be downward. Anyway, there you go. So set up your, I like to set up the torque expression, so figure out what the forces are, where they act, whether they're clockwise. This guy here, this torque here is clockwise, right? It tends to make it torque clockwise. This also is clockwise, so it's positive, right? And then this torque here is anti-clockwise, so it's negative. That's why those signs are there, right? Positive, positive, negative, right? If there's angles, use the sine of the angle. If there are right angles, there's no sign. I mean, sine of 90 is 1. And then you bust out your torque expression, plug it into your x and y's. Happy hunting.